Okay, well, welcome to Physics 221. It's funny to say that in week 7, but our first actual in-person meeting, so it's good to see everybody. It figures the week we were going to come back, there was a blizzard, basically. So anyway, we got about a little bit more than half the semester to go. There's about 16 weeks. This is week 7, so that kind of puts it into perspective. Homework 4 is due on Wednesday, so we will devote maybe the last 15 or 20 minutes. If you have any homework 4 questions, we can take a look at those. And then I put homework 5 up a little while ago. It's due a week from Wednesday. So the nice thing about that is it's March, which that means it's warmer, right? So you've got a little over a week to do homework 5, which is on magnetism. So if you're sick and tired of electricity, you've come to the right place. We're doing magnetism starting today. Now, lab this week, and really for the next 3 weeks, it's going to look something like, well, before I change the screen, any questions on this stuff? And then we'll talk about lab. Okay? Let's see. So this is from an announcement I sent out earlier. So there's about 22 people or so in the class, but they only made one lab section, so we got to kind of divide it up into 3, so everybody works by themselves. So this really hasn't changed, other than we did not have a lab last week because of the snow. So if your last name begins with M through P, we'll actually meet in person tomorrow. Now, for some reason, I'm not sure why they did this, they scheduled the lab from 7 to 9, which is usually from 5 to 7. So I will actually be here at 5. If you can't make it till 7, that's fine. I'll still be here. But if you want to come earlier, if this is your lab day, and you want to come in at 5 and do it, that's fine too. I haven't posted what it is yet, but I'll do that tomorrow morning. And if your last name is A through L or R through Z, I'll be posting an online lab that you do through Pivot. Okay? And then the following Tuesday, the R through Z's will actually meet in person, and then we'll have online for the other groups. Now, it's not online like you've got to go to a certain time and be there online. It's like you've done before with Pivot. I'll tell you what the assignment is, then you go to the Pivot and basically do the lab that way. Okay? So everybody's doing the same lab, just not in the same order. Okay? Very good. Any questions about this? Hopefully it's not too confusing. And then the following week, what's exciting about the following week? Spring break. Good. So for whatever that's worth in this environment, at least we have the week off of school. Okay. Any questions about the lab schedule here? Now, you might have sent me an email, can I come a different time or whatever. I mean, I'm just saying this in general. I got a few people that couldn't come one day, they want to come the next and things like that. So just let me know beforehand. We can't have too many people come in for lab because we've got 8 stations basically. Okay, and for lab, if you're meeting in person tomorrow, it's in room 220, which is right down the hall a little ways. Okay? Any questions on that? Okay. By the way, I said homework 5. There's probably 10 homework, so that's about the halfway point. Let's take a look at the schedule here. So course home. Actually, I got to go to content. Yours looks different, so let me do it like you see it. Okay, content. And then the syllabus, just to kind of see where we're at in the semester. Okay, so this is, looks like the 22nd. We're a little bit behind here. We had a snow day and stuff, but we are starting chapter 24 today. So somewhere up here. So we're about one behind actually. So chapter 24 is what's on the agenda. It's a long chapter. It's magnetic, how to make magnetic fields, and then forces on moving particles in magnetic fields. Some books do that as 2 chapters. This book does it as 1 chapter. So it's kind of a long chapter. The homework is a little bit longer than usual too. It's got 14 questions. Okay, so here's what's coming up. We've looked at circuits. We'll talk about any homework questions you have today. We're starting magnetic fields, forces, and then we'll get into induction. And this kind of relates how you can make electricity from magnetism, basically. So the lights are on in the room for this idea of induction. If you have a wireless charger for your phone, you're using induction. So changing magnetic fields produce changing electric fields. If you're getting a signal on your cell phone, it's because of electrical and magnetic fields hitting your phone. Okay, so pretty cool stuff coming up here. Excellent. And then, so that's for the next 3 weeks. We already had that week. This week, next week, and then review for exam the week after next, and then it's spring break. Okay? And that'll mark about the 2/3 mark of the semester, actually. Okay, good. So fun stuff, magnetism coming up, and then if you notice down here, what's coming up after the second test, we've got optics. So this is using lenses and mirrors, wave optics, light behaving as a wave. This is light behaving as a ray. This is light behaving as a ray, and then we'll have light behaving as a particle, actually, too. Okay. Very good. Any questions on what's coming up here? All right, so a couple of fun weeks. So let's get into chapter 24, and then the last 15 or 20 minutes, any homework questions you have from homework 4. Okay, magnetic fields and forces. So the goal is to learn about magnetic fields, and really there's 2 sides to this. How to make magnetic fields, and then what happens to a moving charge in a magnetic field. We'll see that in this chapter. Okay, so if you go outside with a compass, why does it point to the North Pole? We'll talk about that today too. Okay? It's really, the needle of a compass is a magnetic dipole. Here's current flowing through this loop, and it's producing a magnetic field. So there's some iron filings strewn about. Current's flowing through this loop. Turns out moving current produces a magnetic field. So the iron filings line up with the magnetic field produced by this. Okay, so currents make magnetic fields. And here's some interesting things that happen when charged particles move in magnetic fields. So the Earth has a magnetic field. Moving charges encounter the Earth's magnetic field. They wrap around the magnetic field lines. They're going in a circle, so they accelerate. When they accelerate, they give off light. So that's what you're seeing here. If you've ever been close to the North Pole, maybe you've seen those, or in Canada or something like that. Anybody actually have seen these? Yeah, like to, yeah. They were reporting that we might be able to see some here a month or 2 ago. I wasn't able to see it. If you go to Norway and Finland and stuff, this is kind of a common occurrence. They're way up there. Okay, so the borealis happens at the South Pole too. So this is the northern lights that we see here. Okay, good. So that's what's coming up. It's almost like magic, if you ask me, magnetism, right? When you're a little kid, you think about it, right, with magnets and getting them to stick together. So when I was in West Lafayette teaching this class as a TA, some students got really excited about it, and you can buy really powerful magnets online. I don't know if you know this, but they would buy such powerful ones, and I don't know what they were doing, but they sometimes would crush their hands accidentally. Put a north and south magnet on their hands, it would stick together, and literally they would break bones. So be careful also. It could be fun, but be careful. We've got some pretty powerful ones in the lab room we'll show you too. They're kind of stuck on the metal part of the wall. Okay, so magnetism. There's a series of experiments. We can look and see how magnetism and electricity are the same, are similar, not the same, and then how they're different. So if a bar magnet is taped to this cork, as you can see in the picture here, it aligns itself with the approximate north-south direction if you have an external magnetic field. It turns out that the Earth's geographic North Pole is actually the Earth's magnetic South Pole. So that's why the bar magnet will line up with that. And we'll see why that is in a few slides from here. Okay, so there's always going to be a north side and a south side. That's what the compass needle is. It's a little magnet. Okay, so this is similar to electricity. Remember we had opposites attract, likes repelled. So for a magnet, a north side and a north side will repel, but a north side and a south side will be attracted to each other. So that's how it's sort of similar to electricity. One difference is, though, with electricity, you could have a positive charge by itself, or you could have a negative charge by itself. With magnetism, you always have a north and south pole together. So it's always a magnetic dipole. So if you cut this in half, you don't get a north and south by itself. You do get two small magnets, south-north, just like you see in the picture. So these always occur in pair. North and south always come together. Now, in theory, there should be a magnetic monopole, and the search is on for the magnetic monopole, but nobody's ever found one. Every couple of years you hear like, oh, we found it, we've discovered it, but it turns out that nobody really did. In theory, though, it would make all the equations look so nice if there were a magnetic monopole, but so far nobody's discovered one. If you find one, let me know. Okay. So we can have these magnets attract different objects, just like we did with electricity, right? You could charge something up, bring another charged object close to it. If they had opposite charges, they were attracted to each other. We saw some examples of that. Same with magnetism. So here's a north and south side magnet, north down. This could pick up paper clips. If you bring the south side, this could also pick up a paper clip. Basically what you do is magnetize the paper clips when you bring them by a magnet, and then you can have this occur. It doesn't work for all metals. Here's like I think this is supposed to be a copper penny. So copper, you can't magnetize very easily, so there's no force here. Okay? So if you remember what we did before in the notes, you had this electroscope, and here's some gold leaves hanging. If you brought a charged rod close by, the leaves would actually separate or come back together depending on what kind of charge you put here. It doesn't work with magnetism. So this is an example how it's different. You can't get these leaves to move apart. Okay? Oh, by the way, the first exam has been graded and the scores are up, so you can take a look at that. I'm not quite sure what the average was. I meant to look and I forgot to, but I'll let you know. So the next test will actually be in person, and it'll be here, so it won't be online. You don't have to worry about uploading work and trying to type it all out and all that. Okay. So what do these experiments tell us? Magnetism is not exactly the same as electricity. There's some similar ideas, but it's not exactly the same. Okay? Later on in the next chapter, we'll see how you could use electricity to create magnetic fields and vice versa. Okay? It's also a long-range force, just like if you had a positive charge and a negative charge, they don't have to be touching each other to be attracted to each other. Same thing with magnets. They don't have to actually touch each other. The closer they are together, just like with electricity, the bigger the force between them, though. Okay, this is a difference, though. There's always a magnetic dipole, never just a north and south by itself. Now we could build an electric dipole, and we actually did, by doing this. Remember, a positive charge, the electric field was away from a positive charge. And you could have that, a positive charge by itself. Now if you put a negative charge close by, this is a dipole. So electric field lines go into a negative charge. And then you see like this behavior. So this looks like what we just saw for a magnet. So the positive kind of is like the north side, and the negative is sort of like the south side. Okay. Okay, so the poles of a bar magnet can be identified using a compass. So if you bring a magnet close to this compass, the compass is actually going to deflect. Just like this next picture. Whoops. Well, it's coming up anyway. So if you brought a bar magnet close to this, you could use the compass to figure out which direction the magnetic field lines are going. I think we're going to do a magnetism lab in person. We've got to figure it out because there's only a certain amount we can do. Where we actually have a bar magnet, we bring these compasses around it, and you can plot out what the magnetic field lines look like. Okay. And again, only certain materials can be magnetized. Iron's a good example. The paper clips down there. Okay, so in class what we would usually do with these is vote on these. And I would give you a sheet of paper that had A, B, C, D, and E on it, but we don't have those yet. Maybe I'll try to get some made. So maybe we could work on this one together. If a bar magnet is cut in half, you end up with... Now I think the notes that you have, unless I made a mistake, don't have the answers to these kind of questions, if you've looked through there. So when you come to class or watch the videos, then you get the answers. So if you were to cut this magnet in half, what would you have? Well, we know it's not unmagnetized, and we know now it's no magnetic monopole, so it can't be this one. So which one could it be? So essentially, from the picture that you saw before, if you cut this in half, you get two small magnets. So if this was north to begin with, when you cut it in half, this one's going to be south. This was south to begin with, so the new magnet is going to have a north up there. So it looks like it's going to be choice C then. Okay, good. So take one magnet and make two magnets out of it. Yes, just like that. Can you hold that up just so everybody knows what I was talking about? So I'll try to get some more of these made so you can vote on it. It's I like to call those analog clickers. You know what clickers are? Yeah, this is an old school clicker. You just hold it up. Nobody sees what you're voting for because you just have it in front of you. Okay, very good. So every magnet sets up a magnetic field around it, just like a charge that we saw before. Positive charge had an electric field going away from it, negative charge towards it. Magnets set up a magnetic field around it as well. So then if you bring a compass close by, it feels the magnetic field of whatever's producing it. Could be a bar magnet. We could make electromagnets also. So this was with electricity. If you had an electric field and you had a dipole here, the force on the positive part of the dipole would make it move up. This would make it move down. Experiences a force because it's in an electric field. So it would rotate, and its electric field lines up with this external electric field. So these lines you see here, that's some sort of external electric field that's being applied. And then you have this dipole in an external electric field. So pretend there's no electric field, the dipole's just sitting there, you turn on this electric field, and now this atom wants to rotate. Okay, so electric dipole experiences a torque because it's a force at a distance, and it'll rotate and line up like that. Okay, this is kind of a synopsis of what I've said. Same thing happens with magnetism. So if you have a compass just sitting here, so sitting here it's just like this, you turn on some kind of external magnetic field, that's what the B is here. Oh, by the way, magnetic field, the symbol is B. If you turn on this external magnetic field, then this compass needle wants to line up with it. Okay? So with the Earth, the geographic north is actually the magnetic south. So magnetic field lines are going into the North Pole, so a compass needle lines up with it that way. Okay? That's the magnetic north. Sorry, magnetic south now is the North Pole. It didn't used to be like that. Always, it changes sometimes. More about that later. Okay, so because the magnetic field has both a direction and a magnitude, we can call it a vector. That's why you see the little vector sign above it. That just says, remember, consider the x direction separately from the y direction. Okay, good. Just like the electric field had a x part and a y part. Okay, so the direction of the magnetic field is the direction that the north side points to because it's lining up with an external magnetic field. Okay, the bigger the magnetic field, the more torque it experiences. As you can see over here. So this compass is closer to the magnet. It experiences a stronger magnetic field because of the magnet. This one, it's farther away, so it says here it turns more slowly because the magnetic field is weaker because we're farther away. So here's the north side of a magnet. Magnetic field's going away from the north side, so this compass is lining up with it. This works really well too. We've just got bar magnets. They're about this big. And you could put compasses around it and it lines up really nicely. Okay. We don't usually think about it, but we're walking around right now going through the Earth's magnetic field. So, I mean, lots of interesting things can happen. And it looks something like this. So in this picture, they threw in some iron filings, which are then magnetized by this magnet, just to really emphasize what it looks like. But you can kind of see it going out of the north into the south. So this direction. So same thing's happening inside the magnet. You can't really see it in this picture because the filings aren't there, but that's what's happening. And you can see the compass needle is lining up with the magnetic field lines as well. So away from the north into the south. So you can take a bunch of compasses, put them around, and plot out what the magnetic field lines actually might look like. Okay, good. So the magnetic field of a magnet points away from the north and towards the south. That's the key here. Just like with electricity, it was away from negative charges towards, away from positive charges towards negative charges. Okay, farther you are away, the less the strength is. Okay, so just like electricity in that regard. Okay, good. So the magnetic field vector representation is useful. It's a good way of thinking about it. One thing we got to get used to is thinking in 3 dimensions now for magnetism. So usually, like on a piece of paper, you know, which way is north? So on a piece of paper, maybe north. What I'm trying to say is up and north are not the same thing. So if you have a piece of paper and it's talking about north, you know, maybe this way is north, but then up is out of the paper. So we're going to have this way, this way, this way, this way, but also up and down. That's what makes it tricky, kind of visualizing what's going on. The reason that we're going to have to think it like that is a moving charge in a magnetic field experiences a force. That force is perpendicular to the direction that it was moving and the magnetic field. So there's always going to be like 3 ways of looking at it, or 3 directions. Okay. New parts of your brain might be used, and you'll feel a little tingle there. Okay. So believe it or not, in lab we could actually make a picture that looks really pretty close to this. Put a bunch of compasses around, and you can see as you go around, this is the north side lining up with the magnet, and then back into the south side. Okay. Okay, so here's one. Let's see if we can figure this out. We'll work on these together today until I can get some of these things printed off. A compass is placed at the black dot. In which direction will the compass needle point? It's probably hard for you to see it on this, actually, isn't it? Yeah, it's too, the color's too light. This is north, this is north, this is north, and this is north. And the choice is not E. It's not 0. Okay, good. So good, north side of the magnet, so we would vote it's going to be pointing away, right? Away from the north side. Right there. Okay. Good. So just to refresh your memory too, or show you where some things are, we go back to the class. So PowerPoints, this is chapter 24. Now if you want to, if it's an in-person class and you're coming, you can print this thing out. I mean, there's a lot of slides, so don't print one per slide, but you can, if you wanted to, let me just actually open it. Print them out like 6 per page, and then it's not so much. If you wanted to, you don't have to. I'm just showing you all your options. So when you come to class, you have the notes here. You can make comments by them, however you want to do it. They're up there for you. So again, completely up to you, however you want to do it. I know a lot of people, if they bring their laptop or their tablet or whatever, will go through them and write notes right on their screen. So it makes it convenient. So anyway, that's there for you. I guess whenever I go to something like graduation or something, I like to have the notes there so I know what's coming up. Or an office meeting, like here's the agenda. Are we almost to the end? So this is kind of like that for you. So you know what's coming up. Okay, very good. So choice B, pointing away. Oh, so this one's a little trickier. A compass is placed at the black dot. So here's a magnet. We're putting a compass here. In which direction will the compass needle point? So this is to the left, to the right, down, up, and it's definitely not 0 because there's a magnetic field there. Okay, so again, you got to think it's coming out of the north, going back into the south. So it's going to be going to the left, right? Correct, I mean? Good, so that's what we have there. There's a trickier one coming up in a second, after this maybe. So let's see what we have here. Drawing the magnetic field lines of a bar magnet. You could take a compass and just go around. Just the key is, I guess, a couple of keys. Leaving the north, going into the south. The closer you are to the bar magnet, the stronger it is. The closer the lines are together, just like with electricity, the stronger the magnetic field is. Okay? Good, so here's a single bar magnet, and you can see what it might look like. You can take a couple of bar magnets and put them together and change what the magnetic field actually looks like. But here's just one, what it looks like. Okay. Here's a north and south, actually. So same idea. We're leaving the north side, going into the south side. So pretend you've got one there by itself. It has its own thing going on. You bring the other one in. Now that the net magnetic field is a combination of both of these. So then you have a magnetic field between them going across like this. Okay? So you can produce a relatively big magnetic field here because the magnetic fields from the north side and the south side are working together in between here. Okay, so for bar magnets, this is just kind of getting an idea of what magnetic field lines actually helping to visualize what they might look like. We don't really have a formula for calculating the magnetic field due to a bar magnet that we'll use in this class. They might just tell you what the magnetic field strength is because of one of these, and then you can figure out maybe the force on a moving charge. There will be 3 different situations where we could calculate the magnetic field. So for a long straight wire, for a circle, and then for something called a solenoid, we'll actually be able to calculate the magnetic field. Okay, so right now we're still kind of getting an idea what it might look like. Okay, good. A couple of norths together. In between here, they tend to kill each other off. And we still have the going from north to south, going from north to south idea. Okay. This is what a refrigerator magnet actually looks like. It's a bunch of these horseshoe magnets put together. North-south, south-north, and then you can kind of see what the resultant magnetic field lines might look like. Okay? Did you know refrigerator magnet was so complicated? Yeah, so that's what we have going on. Yes, that's a good experiment to do, yeah. I was going to say something. Go ahead and tell what happens.
Since you have a north line and a south line parallel, then if you rub them together, they'll go to a small place where they repel each other.
Ah.
And so it feels like they're going over bumps.
So they're
Repulsing a little bit of attraction, a little bit of repulsing, a little bit of attraction.
So I don't know if they could hear it. So if you have a north and south, same thing with the other refrigerator magnet. There'll be places where north and south are together and they're attracted. There'll be a place where you have a north and north together as you move it, and those are repelled. So it feels like you're going over bumps for that reason. Yeah, cool. So try that if you got a couple of those when you get home. Okay, so the south pole of the Earth's magnet is located near, but not exactly with the geographic north pole. So it's tilted a little bit. But generally speaking, the north geographic pole, the north pole, is actually the south magnetic pole. So when you have a compass and you go outside, remember the compass wants to line up with the field lines. So if you have a compass and you're here, it wants to point this way along the magnetic field lines because they're coming out of the north and going into the south. Okay, so it doesn't quite go because the tilted the Earth, but here's where it is. Okay, good. So lots of creatures actually use the Earth's magnetic field to navigate. I saw a thing on PBS. It's these turtles. They hatch and they run to the ocean. I think it's on the Atlantic Ocean. Only a small fraction of them make it because birds swoop in and get them and eat them. But they start off running for the ocean. I'm putting it in quotes because they're little turtles. They're not that fast. They make it there, and then they swim for months and months and months all over the Atlantic, North Atlantic, and then they come back to the exact same beach. So how do they know to get back to the beach? So you might say, well, it's instinct. And probably maybe some of it's instinct, but really what they're doing, people that study this thing, is using the Earth's magnetic field to navigate their way back. Okay. I don't think they're thinking, all right, I got to calculate which direction using the Earth's magnetic field, but it's kind of built into their circuitry. So here's some magnetic bacteria, strongly magnetized bits of iron. Their bodies rotate to line up parallel to the Earth's field, just like a compass. So they prefer low oxygen environment near the bottom of bodies of water, so they can use that to figure out where they're going to go. Okay, so they follow the vertical component of the Earth's magnetic field down. Okay, good. It's kind of like their own built-in GPS in a way. So you can have a bar magnet with a built-in magnetic field, or you could produce a magnetic field if you have current. So current flowing through a wire produces a magnetic field, discovered accidentally like a lot of things. Somebody just happened to have a magnet by a wire. I think it was actually Faraday, and they noticed that the wire actually was producing a magnetic field. Okay, so you can have a compass with a built-in magnetic field, or you could produce a magnetic field if you have current flowing through a wire. Okay, so you can take a wire and bend it into different shapes and produce different sorts of magnetic fields. So here's a so-called long straight wire. So here's a picture of it. Here's another picture of it. So the magnetic field goes around in a circle. So if current is flowing through this wire, the magnetic field goes around. This is a difference between electricity and magnetism. For positive and negative charges, the field always went away. For a wire with current flowing in it, the magnetic field goes around. Okay, and here's kind of looking down on a picture. Here, we're going to see our first right-hand rule, actually. So I'm coming over here so I could actually do this. I know that current has to be flowing out of this page, this way. The way I know that is the thumb, so I got my hand like this. The thumb is the direction of the current, so the current's coming out. and the magnetic field lines go around this way. So they go in the direction of my fingers. So this is the first right-hand rule that we have. Okay, if current were flowing into the page, the magnetic field lines would be going around this way. Okay, you can see also they're closer together when you're closer to the wire here, and then they start spreading out when you get farther away. Maybe you've seen videos of like a junkyard, people are using a magnet to pick up a car. So the magnet comes over and then picks up the car, moves it over, and then drops it. Like it's a magnet that you could turn on and off. It's an electromagnet. So you magnetize it by turning current through it. It produces a magnetic field. You can move the car wherever you want to, turn the magnetic field off, and then the car drops. So you can pick up huge amounts of mass doing that. So it's pretty neat to be able to turn on and off magnetic fields. You don't have to have a permanent magnet, you could have an electromagnet. Okay, good. Or maybe you can bend it into this shape. So now this is just a loop. So here, current's actually coming out this way and then going back in here. I know that because in the plane here, current is coming out, so that my thumb is the direction of the current, and then then the magnetic field is wrapping around like this. So it's coming out, going back in. So then down here, the magnetic field's going around this way. And then as I go around, it's going, following this path. So here's the wire coming out and going back in. So everywhere inside this loop, the magnetic field is to the right. The formula that we come up with for this shape is just going to be at one location. We'll be able to calculate the magnetic field right in the center of this loop. I mean, you can calculate it at different spots if you took this sort of physics with calculus, and then you can calculate it wherever you want to. But for our purposes, we'll have a formula that will get it right in the center. Okay? Any questions so far? Okay. So this is something called a solenoid. It's a bunch of loops. So they're all kind of working together. So here's current going from one into the next, and they're all connected together. You might have seen something that looks like this. Usually it's like orange wire, really smashed together, small threads. They're actually not touching each other. There's like there's a little coating on them, so they're not shorting each other out. But they're going around like this, and then they're all working together. So this is something called a solenoid. If you have ever had an MRI, basically what they're doing is putting you inside of a solenoid this way, and then they can adjust the magnetic field, and that tweaks different parts of your body depending on what it's made out of, and they can reconstruct an image of what you look like inside. Okay? So more about MRIs in this chapter as well. It's almost like a miracle, right? You could see inside somebody's brain just by putting him in a magnet, turning on the current, and then using a little quantum physics to figure that out. Now the neat thing about a solenoid is the region we'll be able to calculate the magnetic field is in here, as I said, and it's uniform. It's a nice constant magnetic field inside. So we'll just look at the inside. We talked a lot about capacitors with electricity because it had a uniform electric field. We can do the same thing with solenoids because it has a uniform magnetic field. Okay. Okay, very good. So magnetic field lines due to currents have no start or end. You can see they were just loops like that. So the field lines here, we didn't see them before, but they're actually going through the magnet. So from north to south and then back through. So same thing, like continuous loops. Electric field lines radiate out. These are always in some sort of loops, closed curves. Okay, good. So this looks like a lab that we do as well. You can figure out which direction the current is going by having a wire, putting some compasses around it, turning on the juice, and seeing which way these compass needles deflect. So here, current is flowing up, magnetic field lines are going around this way. So you can see the north side of the magnets are all pointing that way then. If current were going the other direction, down, then the magnetic field lines would be going this way, and the compasses would be lined up the other way. The farther you get away from the wire, the smaller it is. But if you're close, you can really see this happen. So in the lab here, when we do this, they're basically pointing north before you turn on the power because of the Earth's magnetic field. You turn on this current, you overcome the Earth's magnetic field, and the magnetic field, because of the wire, dominates. All right, good. Again, current flowing down, they're going in the other direction. Okay, so I already kind of mentioned this, but this is the first right-hand rule that we have. So this right-hand rule, what's the purpose of it? It tells you the direction of the magnetic field due to current flowing through a wire. So put your thumb in the direction that the current is flowing. You know, kind of like the old days where we used to shake people's hands. Just move your fingers back this way a little bit, and then magnetic field lines curl around like that. Okay, so make sure you use your right hand for this or you'll get the opposite answer. So again, we're going to be talking about 3 dimensions. So how do you talk about into the page and out of the page? So this means into the page. So this would be a wire with current flowing into the page. So if you were to shoot an arrow, you would see like the feathers. You know, that's what your view would be. And that's away from you. Like into the page. Now if somebody shoots one at you, you see the tip of the arrow coming at you, and that's out of the page. And then you quickly grab it. Okay. So this means all these dots mean out of the page, all these X's mean into the page. The more and more X's you have, that means the stronger it is. Less X's, weaker. Same thing for out of the page. Okay, and then we still have left, right, up, and down. So this is the 3rd dimension we're looking at here. Okay, so does this make sense? So current here, this is telling you the direction of the current. So that means it's into the page. So what I'm doing is putting my thumb into the page, and then the magnetic field lines are going around. So thumb is current. The way my fingers curl is the direction of the magnetic field. Okay, good. It's a lot easier for me. You're watching me do this, but I'm standing in front of it, so it's easier for me to see it because I'm literally right there. Okay, so let's try to figure out which direction this current must flow. So a long straight wire extends into and out of the screen. The current in the wire is. So we've got these magnets around here. Okay, very good. And we have to figure out which way the current's flowing. Let's just pick into the screen first of all. We got to check these out, see which one it is. By looking at it, I don't know. You have to check it out. Let's pretend that it's into the page. So it's not into the page, right? Because then they would be going the other way. So it's got to be out of the page. And then you can see they would go that way. Okay? So there's definitely a current because you can see they're lined up in that circular way. Right-hand rule, yes. So point P is 5 centimeters above the wire. Okay, so point P is like here. Like here's the wire. The point that we're talking about is here. It looks like it's on the wire, right, because it's a screen. But this point is actually out here, like where the tip of my finger is. We want to know the direction of the magnetic field out here. Okay, so you have to try to figure this out. Okay, very good. So current is going this way. In this plane, it would be down, right? Because it's always going around. Out of the page, around this way, down, into the page, 5 centimeters into the screen, back up, and then back this way, because it's going around. So right here in the plane, it's got to be down. All right, do you see that? Okay. All right, great. And then we'll come back to this one because we don't actually have the formula to calculate the strength of the magnetic field yet. Okay, so here's a current carrying loop. So with the loop, what we're going to have, just looking ahead, is a formula to calculate the magnetic field right in the center of the loop. So here's a nice picture of what's going on. It's basically this, but just looking at it in 2 dimensions. So current's coming out, that's what the dot means. And then it's going back in. So you can line up your finger with the current. So inside the loop, it's going to be to the right, to the right, to the right, to the right. You know, all the way around, it's to the right. So the magnetic field's going to be this way. Okay? Luckily, you have a 50-50 chance, right? It's either left or right, but just try and see which way it is. Okay, here's a look of it this way. So current in the plane of the screen coming out, or sorry, current's going this way. Magnetic field coming out and going around, right? Because everywhere it's looping around. So it's out, back in. Everywhere you go, it's like that. So inside here, they're all adding together, and we could calculate again how much it is right in the center. Okay, and that's what we'll have. The magnetic field's, you know, everywhere. It's a lot weaker on the outside than the inside, and you could, in theory, calculate it anywhere you want to, but for our purposes, we will have a formula for right in the center. Ooh, okay, so let's try this one, see what we can come up with. I feel like I'm cheating because I can come right up here and you have to kind of use your imagination a little bit. So the following diagram shows a current loop perpendicular to the page. So this is a slice just like we saw before. Current's coming out of the top and then going back here. What is the direction of the magnetic field at a point in the center of the loop? Okay. So it's always coming, the current's coming out, right? That's what this means, out. So the magnetic field's always going this way. So it's going, add them all together, it's going to be going to the right. Okay? Good. If the current was going the other way, it would be going to the left. That's how we know it's got to be, like if they said the magnetic field's to the left, which way is the current, then you'd have to go around the other direction, right? Then if they told you it was to the left, then if you went around this way, it would be the opposite of this situation. Okay. So there are many applications of magnetism for which we would like to generate a uniform magnetic field. MRIs are one that I mentioned a little earlier. So a field that has the same magnitude and same direction everywhere is uniform, and that's what a solenoid will give us, a nice uniform magnetic field. Okay, good. Might look something like this actually. So it's a long coil of wire with the same current passing through each turn. It looks like it's kind of like shorting out, right, because they're next to each other, but they're insulated from each other, these little wires. And you might have seen something like this actually. Usually it's orange and small, maybe in a motor or something like that. So the field within the solenoid is strong, mainly parallel to this axis, and uniform right in the center. It doesn't even have to be right in the center, but what I mean is inside the solenoid, not outside. Okay, so it looks something like this. So I had this ringing in my ears, so I got an MRI actually. So they put you in here, and I don't know what I was thinking, like, oh, they just put you in there, they turn it on, and then like 30 seconds later you're done. But it actually takes like 20 minutes or a half an hour or something like that. And it's actually loud because they're providing a whole bunch of current to do this, and it's like all this noise, and they want you to be in a uniform magnetic field, so you're really in something like that. That's what I kept thinking the whole time. So anyway, here's an application of it. They didn't find the reason for the tinnitus. That's ringing in your ears. It's not that bad. Anyway, so let's see what we have here. What is the direction of the current in this solenoid as viewed from the top? So they're telling us the magnetic field is this way. which direction does the current have to flow? So we have to pick out a section of this and see. So let's just focus down here for a minute at the lower part. Let's pretend that current was flowing this way. Okay? So put your thumb in the direction of the current. So inside the loop it would be down then, right? If current was flowing this way, inside here, the magnetic field would be down. But it's not, right? They're telling us that the magnetic field is up. So would it work out if current was flowing the other way? Let me do the same thing. I'll just pick this spot down here, this part of the wire. So if current is going this way, then it would be, the magnetic field would be in that direction. And you could pick any loop you wanted to. I just picked the bottom one here. And it's all working in the same direction. Okay, so the current's got to be going this way then, right? For that to produce a magnetic field the way that we see it. Let's make sure that we're correct. Yep, counterclockwise. So going like this. All right, it takes some getting used to, I think, right? So in the next test, you'll be able to use the right-hand rule, and the test will actually be in here, so you can write a big R on your hand. There's always somebody that accidentally uses the left hand. Okay. So we can actually calculate the magnetic field for those 3 different situations I talked about. So this is for a long straight wire. It's not like some kind of law, but this is a really good approximation. It's good up to 99% as long as the length of the wire is 14 times the distance away from the wire, which it almost always is. So as long as this length is 14 times how far you're away, this is 99% accurate. So all the situations that we have will be that situation. Okay, so the magnetic field, mu 0 times I. So mu 0 is a new constant that we haven't seen before. 1.26 times 10 to the negative 6th Teslas. So Tesla is the unit of magnetic field strength. Oh, as it says up there. So T for Tesla times meters divided by amps. So with Physics 220, you know what meters and seconds are, kilograms. You have a lot more intuition for stuff in Physics 220. And then you come to Physics 221, electricity and magnetism. All right, maybe you heard of an amp and a volt, and maybe even an ohm, but they're less familiar maybe. Magnetism is even the next step up from that because now we have Teslas thrown in. But what it does is it measures the magnetic field strength. Meters you're familiar with, and then we have amps thrown in. Okay, so we're making some real progress when we start talking about Teslas. So in this formula, I is the amount of current that's flowing, and then R is the distance that you are from the wire. This is the magnitude of the magnetic field. To get the direction of the magnetic field, that's what you have to use the right-hand rule. So this gives you the magnitude. The first right-hand rule will give you the direction. Let me actually draw a picture of this. So on the next test, you'll be able to make your own formula sheet. That's the way it works. One sheet of paper, both sides, put whatever you want on there, and you get to use that during the test. So you'll put formulas, you can put example problems, words of encouragement, whatever you want to put on there. So here's the formula. Here's current flowing. R is the distance away from the wire in the formula. So that's what R is. Not like the thickness of the wire or anything like that. Literally, it's the distance away. And then U0 is that new constant that you saw. I believe it's to the negative 6th, but let me see. Yep. Okay. Now this gives you the magnitude. What's the direction? Well, if current is flowing like it is in this picture, up here it's out, because it's coming out of the wire. Down here the magnetic field is into the page, because it's going around. If current were flowing the other direction, the magnetic field would just be the opposite. Okay, so as you start to think about the next test, you can as you go along, start building your own formula sheet. I mean, something like this would be good. Here's the formula. That's perfectly good. What do these different things mean? You could even write B, magnetic field. U0 is that constant. I is the current. R is the distance away. That sort of thing. Maybe have a little picture. Kind of organize your thoughts. Good. So if we have a wire with current flowing through it, it's going to produce a magnetic field. That's how much it's going to be. Whoops. Good. Here are some typical magnetic field strengths. So the Earth, maybe start with the Earth, 5 times 10 to the minus fifth about on average maybe. If you're 1 centimeter away from a 10 amp wire, that's a lot more. A whole order of magnitude and 2.5, so 25 times more. 1 centimeter from a 10 amp wire, the magnetic field's 25 times what the Earth has. Refrigerator magnet, surprisingly, is really big too, right? It's got to hold up your whole shopping list and all that, so it's got to be pretty big, right, to do that. We have a chalkboard refrigerator, so we don't have to worry about that. 100 turn coil, 1 centimeter diameter with 1 amp. So this is a bunch of loops together. 1 times 10 to the minus 2. Surface of the sun, like around 0.1 teslas. Near a rare earth magnet, 1 Tesla. So when you start to get up into the 1 Teslas, these are really, really big magnetic field strengths. So if you do buy one of these really powerful combination magnets, be careful because they really are powerful. Okay. So just to give you an idea of different strengths. So if you were to graph this, the magnetic field is mu 0 I over 2 pi r, so it's inversely proportional to the distance away. Not r squared, just r, so it drops off kind of like this. Okay. Twice as far away, the magnetic field strength is half as much. With electricity, with a charge, if you remember, if you were twice as far away, it was 1/4 as much. So this is inversely proportional, not to the square, just to 1 over r. Okay, good. So the total magnetic field at any point is, it says the vector sum. That just means you've got to add up the x parts and the y parts. So if you had a magnet here, it produces a magnetic field. You have a wire here, it produces a magnetic field. What's the net magnetic field here? Well, you'd have to figure out how much of the bar magnet is in the x direction, how much of the magnetic field because of the wire is in the x direction, add them together. Do the same thing with the y part, and then you can, x part squared plus y part squared. Figure out the net amount. I mean, this is just in theory. We're not going to be doing that in this class, but we will do it for a couple of different shapes, maybe a long straight wire with a loop in it or something like that, or a couple of long straight wires. What's the net magnetic field in between them? Okay, so just like electric fields where you had to look at how much one was contributing, how much the other was contributing, add them together. It'll be the same thing with magnetic fields. Okay, so I wanted to leave enough time for any homework questions, so maybe that could be enough for today. Actually, it's 74 slides, that's kind of a lot. So for the rest of the chapter, I'll make a video Wednesday or Thursday and put it up. So tomorrow, if your names were on the list, I'll see you tomorrow. If you can be here at 5, I'll be here at 5. If you can't make it till 7, that's fine also. I'll still be here. And so that's all for the new stuff. So the next part is kind of like recitation. So if you were taking the class in West Lafayette, if they're meeting in person, I'm not even sure they are for recitation, you would meet with your recitation instructor once a week and go over homework, anything you want to. So usually with that, unless there's a quiz, you just go to that when you want to get help or work on homework questions. So if you don't want to stay for this part, that's completely fine with me. But if you have questions you want to look at homework for, stay for that and we can work on some of your homework questions. Okay, so that's the new stuff. If you want to stay for the homework part, that's perfectly fine. If you don't want to, I won't be mad if you don't stay. Totally up to you.